Hi everyone, my name is Branislav and the title of this talk is Desired State, How React, Kubernetes and Control Theory Have Lots in Common. It's a talk where I simply want to share with you a certain type of abstraction that I've come across working across the stack. It's a model that comes up again and again in various areas of computing, from UI engineering to infrastructure management, databases, programming language theory, and elsewhere. For lack of a better term, we could call that abstraction desired state, but that name only describes a part of it. I'll go through some of the ways that we can look at this abstraction and show some examples of where it's used. My hope is that by the end of this talk, you'll be able to not only spot this abstraction in the tools and APIs that you encounter, but also be able to assess whether it's worth using in your projects and products. This talk has 8 parts. I will start with some general motivation and go through a simple example of how we can look at systems which are even outside of our domain with this abstraction in mind. This will give us some general principles that underlie this model. Then I'll present several different angles from which we can look at this abstraction, with examples from well-known tools like React, Kubernetes, and Terraform. At the end, I'll talk about the things you should think about when applying this abstraction yourself, and we'll of course have time for some questions. Like I mentioned, my name is Branislav, and you can find me on GitHub over here. I work for a company called Sesam here in Oslo, where we create a product which helps companies make their siloed systems talk to each other, merge and transform data, and manage their master data. We are also hiring, so if that sounds like something that would interest you, don't hesitate to come by after the talk or go to our website. Let me start by talking a little bit about why it's sometimes useful to try and zoom out and evaluate the tools that you encounter and examine why they work the way they do. It is said that all models are wrong, but some are useful. We as developers constantly deal with models, most intimately in the case of our own internal mental models of how things work. I think it can be really useful to look at different fields, industries, or areas within, and try to spot connections between concepts across them, and find common models. Sometimes you find seemingly unrelated things which rhyme with each other. Your models will never be perfect, but that's not the point. They help a lot with learning, as new things can be quickly mapped to your existing mental models. Kind of like when learning new languages. The more languages you know, the easier it gets, whether that is human languages or programming languages. The syntax might change, but the underlying model often doesn't. It allows one to think a bit more clearly about things, especially when the brain fog sets in a particularly long Teams meeting. The desired state model I want to describe in this talk can be found in common tools and libraries within front-end web development, back-end web development, databases, infrastructure, graphical user interfaces, and others. It's a model of an abstraction, but it's closely tied to the notion of an interface, as the abstraction fundamentally changes how we as developers or our users or other systems interact with the system. But what even is an abstraction? The authors of this wonderful book, Concepts, Techniques, and Models of Computer Programming, define it as any tool or device which solves a particular problem. That's a very general and correct definition, but I especially like the take of Joel Spolsky, who simply states that abstractions are pretending. He says, "What's a string library? It's a way to pretend that computers can manipulate strings just as easily as they can manipulate numbers. What is a file system? It's a way to pretend that a hard drive isn't really a bunch of spinning magnetic platters which can store bits at certain locations, but rather a hierarchical system of folders within folders containing individual files which consist of strings of bytes. Abstractions are central to what we do. I find that the most difficult work for me, but also the most rewarding, is not writing programs, but rather designing abstractions. Programming a computer is primarily designing and using abstractions to achieve new goals. It's exciting when you can build something which hides away some of the underlying complexity and presents a simpler interface for whoever or whatever is using your system. This was all rather abstract, so let's get to an example from everyday life. Consider an ordinary elevator. You come up to it and you see two buttons with arrows pointing up and down. I don't know about you, but growing up, my brain always interpreted the up and down arrows as I want the elevator to go up and I want the elevator to go down, instead of I want to go up and I want to go down once I get on the elevator. In other words, I wanted to directly control the cabin. To this day, it sometimes takes a little bit of my mental capacity to remember this. To a person coming to an elevator, what do these buttons represent? They are the elevator's interface, a device which allows the user to communicate with the system. We could also think of a user as just another system, and thus arrive at a generalized definition of an interface as any point where two systems interact. Now, my possible confusion could stem from the fact that an arrow pointing somewhere can both mean I want to go there and I want this thing to go there. And there's probably not that many people who share this confusion. But let's ignore the question of interpreting the user interface and try to compare the two approaches as if they were both entirely valid. What could we call these two approaches? In my kid brain approach, I wanted to tell the machine exactly what to do. In other words, how to achieve what I wanted to do. I wanted to give it commands. Someone with knowledge of Latin would then maybe suggest we call this an imperative approach. In the other approach, we simply tell the machine what we want to do and we let it figure it out. We declare what we want. So maybe we could call it a declarative approach. Using an imperative interface, we tell the machine exactly how to do what we want, how to get to our floor. Using a declarative interface, we just tell it what we want to do. It then runs a small piece of logic that determines how to actually move the elevator. That piece of logic has to account for several things, such as where the elevator is right now, which floor the caller is on, and so on. If the elevator is above us, it needs to go down. If it's below us, it needs to go up. Using an imperative interface, it's actually us who would be responsible for figuring this out. To do that, we need to be able to obtain the information about where the elevator is, which might be potentially provided for us with a display. Though that's not always the case, which quickly disproves the validity of my kid brain approach. Only having this piece of state in mind can we decide what command we give to the machine. In the declarative approach, we don't need to know anything about the current state of the elevator. Note that in my example, when using a declarative interface, we are actually providing the elevator with two pieces of information. We want to get on the elevator, wherever it is right now, and also that we want to go up or go down once we get on it. Let's simplify our example for a second by separating these two concerns and focus only on the first one. We signal that we want to get on the elevator. In such a case, all we need is a single button, right? And simple elevators like that, of course, exist. We went from two buttons to a single one. What does that imply? It implies we have less control. Counter to that, the imperative interface gives you a higher degree of control. You can make the elevator go up or go down regardless of where you currently stand. Again, not that it makes that much of a sense in the context of normal everyday elevators, but you could conceivably do it. The declarative approach gives you, in a certain way, less control. The elevator always just goes to us. However, you probably see that that's not the full picture. What my kid brain didn't really think about at all when seeing the elevator buttons is that the entire point of an elevator is that it can service multiple floors. The elevator interface isn't just the buttons on our floor, it's buttons on all the floors and also the buttons inside the actual elevator cabin. Once you have the full picture, you see that the imperative approach would never work. How would you deal with multiple people controlling the cabin at the same time, concurrently? What if you weren't quick enough and from the time you looked on the screen to pushing the button, the elevator just whizzed by you and you sent it further away? What if two people on different floors just kept mashing opposite inputs, making the elevator essentially oscillate in place? What the declarative approach takes away in control, it gives back in being able to fix these kinds of problems. For example, we can simply use a first come, first serve principle to eventually handle all the people on the different floors based on the time when they press the button. But this isn't very efficient. We know that if people from multiple floors want to go in the same direction, we should just stop on the way. Well, what if the user told us beforehand where they want to go? Then we can optimize the operation of the elevator and take on more people that need to go down when the cabin is going down, and vice versa. You could call this piece of information a domain-specific parameter or something like that. In the end, that's why there are two buttons, and that's why they symbolize where we want to go, and not where we want to go, and not where we want the cabin to go right now. In some very tall buildings, you can even choose the exact floor you want to go to before even boarding the cabin, which allows for further optimization of the operation. The point is that by taking away imperative control and adding domain-specific parameters, we are able to optimize the operation quite a lot. The commands to the electric motor can be queued, reordered, and so on. It gives us the ability to make the elevator work for multiple floors and multiple people using it concurrently. It allows us to build better and better optimizations and completely hide the mechanics of the underlying system. Note that the elevator is just keeping on doing the same thing. It's going up or going down, stopping at this or that floor. So something inside has to have direct imperative control of the elevator. Otherwise, it wouldn't matter that we want to go somewhere, it just wouldn't move. A way I like to think about this is that the declarative interface, in a way, wraps around the imperative interface. This wrapping is just really another word for abstraction. It is this type of abstraction that I see everywhere around me. We could call this abstraction desired state. We give the system our desired state, we want the elevator on our floor, and let the system take care of the process of bringing the actual state of the elevator in line with our desired state. In order to do so, it must be able to query the underlying system to obtain the current state, compare or diff it to the desired state, and issue commands to it which update the actual state accordingly. In order to differentiate between the various words, let's use the verb apply for the act of giving the desired state to our system. Let's now generalize these principles. A desired state system wraps an underlying API or system which has an imperative mutable interface and allows its user to specify a desired state for this underlying system. The wrapper is then responsible for figuring out the actual state of the underlying system, comparing it to the desired one that is given by the user, and figuring out how to apply the necessary changes to bring the actual state in line with the desired one. The part in the middle of this diagram where it goes through this loop of observing the underlying system, comparing its actual state, and acting on it accordingly is called reconciliation. As I mentioned in the example, we can think of this abstraction in several different ways. For one, as a declarative interface wrapping over an imperative interface. An interface where the user simply states what they want to do is going to be simpler. It can also be beneficial by restricting the surface of the API and steering the user into some wanted patterns of usage. Many tools also utilize the fact that desired state can be version controlled, which aids in testability and auditability. We can also think of it as a stateless interface wrapping over a stateful interface. But why do we even want to minimize having to keep track of state? It makes systems more understandable and testable. The API becomes simpler and easier to maintain, which means it becomes more reliable. Being able to reason about effects of changes to a particular system is extremely important, particularly when dealing with concurrency. Another way of looking at it is that we are wrapping an API with mutable semantics with an API with immutable semantics. In some cases, this abstraction gives us the ability to treat our underlying system as an immutable object, which cannot change. If something has indeed changed, we can think of it just as an entirely new object. This again helps with reasoning about effects of changes. These are just three of the many possible axes that we can use to analyze a desired state system. And it's useful to keep them in mind as we go through some of these examples. Let's first look at React, which uses a somewhat simplified version of a desired state system. React is a popular JavaScript library for building user interfaces. It lets you define how you want your application to look and behave, all within JavaScript. You define your app as a tree of composable components, which serve as the input to React. The tree defines the structure of the application, while the look is controlled by the various properties applied to the components of the tree, and the behavior might be controlled by various callback functions, which trigger on user inputs or some phase of the component lifecycle. The leaves of this tree represent the actual HTML elements to be displayed. The tree is essentially just a giant nested call of React's createElement function. The first argument to this function is the type of the node that we want to use. This can either be a component which was defined by us, or a leaf node with a specific HTML element. The second argument are the properties we want to send down to this component. And the third argument specifies the children that the component node in the tree should have. This interface makes components very composable, as you are able to quite dynamically pass data, callbacks, and even other components from a parent component to a child component in the tree. This allows React to express many useful design patterns. In order to save typing and brings the syntax a bit more in line to actual HTML, many people use a syntactic sugar called JSX, which just makes the function calls a bit more compact. React wraps around the browser document object model, or DOM, which is a deeply imperative API present in all web browsers. This API lets us programmatically alter the contents of the page. It represents the HTML page as a tree of nodes with attributes, properties, event handlers, and offers methods for querying, creating new elements, appending new children in the tree, and so on. React's component tree has a similar structure. Let's now look at React through the lens of a desired state system. When the page loads, some initial desired state in the form of a component tree is given to React to be rendered. Internally, React keeps a representation of this tree in memory. And whenever the desired state changes, based on the user input or some other triggers, it compares the old state to the new state. This internal representation used to be called virtual DOM, though that name isn't used much anymore. The comparison of states generates a sequence of operations that need to be performed on the actual browser DOM. Generic algorithms for generating the minimum number of operations needed to transform one tree into another have the complexity in the order of O(n) cubed, where n is the number of elements in the tree. However, that's way too slow for React. React has to do these diffing really fast, and so it uses a series of heuristics to compute the least number of operations necessary. This brings the time complexity down to O(n). These heuristics rely heavily on two assumptions. First, two elements of different types will produce different subtrees. And second, the developer can hint at which child elements might not change across different renders with a specific property called a key. This is needed for lists and other places where ordering is important. React also relies on the fact that the properties passed down to the children in the tree are immutable. It assumes that when an object's contents change, so does the reference to this object. React can then do some simple reference comparisons without doing deep diffing and re-rendering components when their properties change. This keeps the UI responsive. The reason I stress this is because the structure of your state and how difficult it is to figure out how to change it when two versions of it are compared can be one of the crucial parts when building a desired state system. The reason React computes the minimal operations necessary is because operations on the DOM are really slow. However, the entire diffing mechanism is really an implementation detail, and React could just choose to reconstruct your entire tree from scratch on every render if it was performant. Now I want to get to the point that React is a simplified desired state system according to our model. Let me therefore digress for a second to some basics of control theory. We say that a closed-loop system is one that is interconnected in a cycle. If System 1 gives signals to System 2, the outputs of System 2 are in some way a part of the input to System 1. This, you might know, is called feedback. A key feature of feedback is that it provides robustness to uncertainty. Closed-loop systems automatically achieve and maintain the desired output condition by comparing it with the actual condition. While feedback has many advantages, it also brings a set of drawbacks. If not designed properly, the system could exhibit instability. This could be in the form of positive feedback, like when a microphone's amplifier is turned up way too high in a room. Furthermore, feedback inherently couples different parts of the system. On the other hand, in an open-loop system, this interconnection is severed. While React is a desired state system within our model, it's actually an open-loop system. React does not keep rechecking the current state of the browser DOM to see if it's in the correct shape. For one, that would probably be prohibitively slow. It also just doesn't need to. Unlike many other desired state systems, React operates with the assumption that it's the only thing touching its domain. It generally assumes that there is no other library or person modifying the page under its feet. You can test this yourself using developer tools in the browser. If you modify an HTML element controlled by React, the library will not try to overwrite your modification unless a parent of the changed element gets re-rendered and the entire subtree gets destroyed. A nice thing about React is that it's built in a modular fashion. The part which talks to the DOM itself is a separate module called React DOM, and can be replaced with different rendering targets, which React called hosts. A different host is used, for example, in the mobile application framework React Native. When writing React Native, you still specify the user interface of your app as a tree of components. However, instead of talking directly to the DOM, React talks to the native APIs of mobile operating systems. It's also relatively easy to extend React with custom rendering targets yourself. A more recent addition to React's API are hooks. They are an interesting design pattern that allows developers to manage state and also side effects within components in a declarative way. I really recommend reading this blog post by Dan Abramov, who works on the React team, where he wraps an inherently imperative API, namely the browser's setInterval method, with a declarative hook. Let's now go a bit further up the stack. Terraform. Terraform is an open source infrastructure as code tool which has the goal of providing one workflow to provision all of your infrastructure. It lets you specify parts of your infrastructure. Most often that means the different types and instances of resources in your cloud provider, plus their configuration as text files written in Terraform's native language called HCL. With these configuration files, you can perform what's called a Terraform plan, which lets you check whether the execution plan for a configuration matches your expectations before you start provisioning or changing your actual infrastructure. When you first run Terraform, it creates a file called tfstate, which stores the current state of your resources. Every time you want to make changes to it, Terraform will go and obtain the current state of your actual resources and report the changes your new plan will make. You can then check if your changes are correct and apply them. In the resulting diff, you can then see what changes your new plan would make, but also whether your actual state has drifted from your saved TF state. In other words, unlike React, Terraform is a closed-loop system. Ultimately, this is because it's optimizing for an entirely different problem. While React needs to have fast updates and can assume that no one else touches its domain, Terraform can spend much more time, and often does, figuring out the difference to the actual state. It crucially cannot assume that the resources it manages are left untouched. Much like you can extend React with different hosts, Terraform has a collection of plugins called providers that you can use. A provider is responsible for understanding the API and the interactions with some kind of service and exposing the resources based on that API. And of course, you can create your own. Unlike React, Terraform has an added complication of how to define what actually is a resource and what is its configuration. A configuration could be specified as its own resource, or it can be just a part of the parent. This can vary between providers, and many resource types even support both. One of the harder parts of Terraform is managing this coupling. Compared to some configuration management tools like Chef or SaltStack, Terraform works on the principle of immutable deployments. When you change your plan, your resources get recreated with the correct state applied. This means that operations can be inherently destructive. Making a configuration change on a virtual machine could mean destroying the original VM and just creating an entirely new one. Which operations are destructive and which are not are defined by the provider. On the other hand, with mutable deployments, you are much more likely to get into a situation where your actual state starts to drift away from your desired state. In other words, changes to Terraform state are idempotent. If you keep reapplying the same state again and again, you just have the same state. If you keep if you keep applying a state which creates 10 virtual machines, you always just end up with 10 virtual machines. Idempotency is a crucial property of a desired state system. Let's now shift gears a little bit from provisioning to container orchestration. You've probably all heard of Kubernetes. It's an open source system created by Google, which is used for automating the deployment, scaling, and management of containerized applications. In order to achieve its promise, it arguably takes the idea of a desired state system to its highest level. Kubernetes manages containerized workflows inside a cluster of machines, which are called nodes. These can be physical or virtual machines. The smallest units of work in the system are called pods, and they can be scheduled to run on these nodes. Ultimately, a particular container with our code is going to be running somewhere on one of these pods. Pods are organized in several different kinds of resources, most often the kind called deployments, but their networking can be defined in a different type of resource called a service, and many other types exist as well. Custom ones can also be defined. Kubernetes itself runs on the side of the nodes as a collection of services called the control plane. The control plane is responsible for serving the API, keeping track of resources, and other tasks which are necessary to keep the system running. The cluster can be controlled by a command line tool called kubectl, which serves as the interface for Kubernetes. While it also offers a sort of imperative-like API, the core of its use is done using YAML configuration files, which are then applied as a desired state to the cluster. We can then look at Kubernetes through the lens of our model. Similarly to Terraform, you give the system the desired state of a particular resource in the cluster, this time in the form of a YAML file. A component called a controller inside Kubernetes then has the responsibility to bring the actual state of the given resource in line with the desired state. Unlike Terraform, this happens continuously. If you try to delete one of the pod replicas in a deployment which has 3 desired replicas stated, Kubernetes will immediately try to spin up a new one. Likewise, if a pod keeps just crashing, Kubernetes is going to keep trying to run it as it tries to keep the actual state in line with the desired state. Another interesting concept from control theory, which comes up in a system like this with continual desired state reconciliation, is called hysteresis. Hysteresis characterizes a system whose behavior does not only depend on some input in time t, but also on the history of this input. You can also think of it as adding some sort of artificial lag to the dynamics of the system. A widely used example of this is a thermostat. Let's say that we want to set the thermostat temperature to 20 degrees. Without hysteresis, as soon as the temperature hits the desired state, the heating turns off. But that means that very quickly the temperature goes back below 20 degrees, turning the heating back on. The thermostat system starts oscillating and quickly turning the heating on and off. When we add hysteresis, the thermostats wait until the temperature is above, let's say, 22 degrees before turning the heating off. Likewise, the thermostat will wait until the temperature hits less than, let's say, 18 degrees before turning the heating back on. This ensures smoother operation and also more reliable operation. In Kubernetes, this concept comes into play when it has to decide whether to move some workloads away from a node whose computational resources are dwindling, so-called pod eviction. A soft grace period can be specified, which means that Kubernetes will wait for a while before scheduling the pod away from the node, because the resource constraints might be a temporary situation. This ensures that the state of the cluster is more predictable and allows for smoother scheduling. Kubernetes is actually made up of many of these controllers working together to bring the actual state close to the desired one. Each controller can act upon one or more resource types. These controllers are actually often nested in a way. A particular control loop which runs inside this component called a controller uses one kind of resource as its desired state and has a different kind of resource which it manages to make that desired state happen. Allow me now one more digression into the basics of control theory. This one comes from circuit design and CPU interrupts. When one system needs to give another system some information over the wire, there are two options. The first one is called edge-triggered logic, where system 1 simply pulses the line with a brief high-voltage spike. The problem with this approach is that system 2 might miss the signal if it's not listening at the time. The second option is what we call level-triggered logic. In this case, system 1 brings the voltage up and keeps it there until it's sure it's been registered by system 2. This approach is more robust as system 2 can just check the state of the wire at any time. You can maybe see some parallels between this and something like event-driven communication versus polling for changes. But let's get back to Kubernetes controllers, where React needs to optimize for fast updates to the browser DOM. Kubernetes needs to optimize the observe part of our reconciliation loop. This is because at any point, a huge number of controllers might need to ask for the state of particular resources. To continuously poll for this information in a distributed system would be inefficient at scale. Therefore, most controllers use a hybrid approach between edge and level-triggered logic called the list watch pattern. In this pattern, the controllers first ask for the current state, then they cache it, and they keep a stream of events open for immediate updates to their cache. Unlike a pure event stream, this system is more robust to crashes and networking issues, as controllers can just reassert the state again at any time. Now let's look at one more way of how we could describe the desired state model, which is a little bit different to the ones I mentioned so far. We could think of it as wrapping an interface of reference semantics with an interface which uses value semantics. Well, what do I mean by that? When we treat objects as values, we assume they cannot be changed. We assume that they are immutable. By object in this case, I mean just generally anything we work with, some piece of data, for example. When programming, we don't have to worry about the difference between the integer 5 and the integer 4, to which we added the integer 1 a bit later. 5 equals 5 either way. It's the contents of the object, in a way, which provide the object identity, and not our reference to it. A desired state system, you could think of it as just a collection of values which we want to exist in the world. Instead of keeping track of the references to some browser DOM objects in React, or containers in Kubernetes, or virtual machines in Terraform, we can simply treat them as values. Values can't be changed, so if we need another one or make a change to one, we simply create a new one. The underlying system ideally takes care of all the mutable logic underneath. In some way, for example, immutable strings in a programming language can just be thought of as a desired state system, where the compiler or the interpreter makes sure to reconcile the value semantics with the underlying memory references in a performant way. Doing this for complex objects, of course, is not easy at all, and often it's not even possible. However, myself, I find it pretty fascinating trying to think about how we could treat something like, let's say, a networking socket or a database or other inherently stateful objects simply as a value. Let's finish off by listing some of the considerations which you should keep in mind when designing a system like this. First of all, you have to ask yourself the question of whether it's necessary. Does it solve an actual real problem? Adding abstractions always leads to more complexity under the hood, and it's important to make the cost-benefit analysis of whether this extra complexity is worth it. A declarative API wrapping over an imperative API might seem a lot simpler to the people using it, but its internal complexity will always be higher. Secondly, is it useful for us to constrain what the user of our interface can and cannot do in this way? Are we sure we want to give the user less control? And do we know exactly how we want to steer the API? Third, do we need an open or closed loop system? In other words, are we the only people in the sandbox? Can we be sure that we are the only ones controlling the underlying API and that no one else is stepping on our toes? Four, do we need to solve the situation that there can be multiple concurrent updates happening to our interface? That might be from multiple users or multiple updates from the same user. How can we reconcile multiple conflicting desired states? 5, can a stateless interface and constraining the surface of the API help us optimize the system in any way, just like it allowed us to do that with an elevator? How do we deal with the fact that things take time? While our API may treat some object or resource as a value, inside of our system, we might need to wait in order to create it, destroy it, update it. How is this communicated to the user, and does it need to be? What's the structure of our states, and how quickly can we compare them? This might or might not be a bottleneck, depending on the structure and the nature of the underlying API. In the example of React, this is definitely one of the bottlenecks. How fast is the underlying API itself, whether that's the observe part or the update part? Generally, a desired state system is always going to be in some way slower than just directly operating on the underlying imperative API. You will always need to weigh the performance hit against the benefits of using such an abstraction. How can we keep track which of the resources in the underlying API we control? This is especially important in a distributed system like Kubernetes, where many control loops run at the same time. And finally, do we need to add any escape hatches to our interface so that the user could potentially drop down to the imperative interface underneath if they need? This might be, for example, for some performance reasons, or simply for allowing the user higher flexibility when using our API. For example, React allows you to directly talk to the browser DOM if you need to. Even though it's discouraged, occasionally it's necessary. Similarly, Kubernetes lets you drop down directly into the shell of a running application inside a pod if you need to do something in there. To conclude, in this talk, I went through my view of what a desired state system is and what are its central principles. I showed you some examples of where it's used and presented what I find are the important considerations you should keep in mind when using this abstraction. The ideas I presented in this talk are nothing new, and most of you have probably thought about these ideas in some capacity before. I hope that by going through it in a bit more of a structured manner, you now have a clearer picture or mental model which helps you in your work. At the end of the day, The world around us presents us with a stateful interface. We are limited by the fact that at the bottom of all our programs sits a simple von Neumann computer with a central processing unit, a data store, and a connecting tube which can transmit a single word between the CPU and the store. That's an inherently mutable and imperative interface. But thanks to some of these abstractions, sometimes, and in limited scope, we can just pretend that's not the case to simplify our interfaces. Thank you for having me, and don't hesitate to ask any questions either now or later. Thank you.